Okay, let's move on to Chapter 2, Section 6, Transformation of Functions. In this section, we're going to cover vertical shifts, horizontal shifts, reflecting graphs, vertical stretching and shrinking, horizontal stretching and shrinking, and then look at even and odd functions. Okay, so in this section, we'll study how certain transformations of functions affect graphs. This will give us a better understanding how graphs function. Okay, so our goal is to start with a fundamental function and see how small changes can affect the graph, so that we can easily get a rough sketch of the graph. Okay, so the first thing we want to look at is vertical shifting. Okay, so we're going to look at what happens to the graph of a function when we add or subtract a constant. Note that in this case, c is a positive constant. Therefore, plus c means that we're adding a positive value, and minus c means that we're subtracting a positive value. So we're going to explore what happens to the original function of f of x as we apply these constants. Okay, so let's look at a really simple example. Let's say we had f of x defined as, f of x is defined as x cubed minus 2x squared. Okay, so the first thing we want to do is evaluate this function at various points so to start to get a sense of what this function looks like. So we can do that by creating a table and plugging different values for x, and then having an f of x over here, f of x. Okay, so we can just try some basic ones. So let's just start off with 0. If we plug in a 0 into here, we're going to end up with 0 cubed minus 2 times 0 squared, and of course the whole thing just works out to be 0. If we plug in a 1, we end up with 1 cubed minus 2 times 1 squared, which is going to end up being 1 minus 2, which is negative 1. And then 2, then that's going to be 2 cubed minus 2 times 2 squared. That's going to be 8 minus 4 times 2 is 8, so this whole thing just becomes 0. Let's do a couple more. Put a 3 there, and then it becomes 3 cubed minus 2 times 3 squared, which becomes 9 times 2 is 18. 27 minus 18 is 9. Good. Okay, we can also try some negative values. Let's try a negative 1. If we do that, we get negative 1 cubed minus 2 times negative 1 squared, which is going to be negative 1 minus 2. Negative 1 minus 2 is negative 3. Okay, so we can try different values, and if we plug in a negative 2, we would just evaluate it at that point. We can come down here and put a positive 4 and evaluate it at that point. Okay, so let's try a couple more with this. So I'm just going to calculate it after some work here. This would be a negative 16, negative 3 there, negative 3, that would be negative 45. A 4, that would be a 32. Okay, so all I care about is the outputs, right? So here are the ordered pairs that are produced. Here we get an ordered pair of negative 3 comma negative 45. Here we get an output of negative 2 comma negative 16. From here we get the ordered pair negative 1 comma negative 3. Here we get the ordered pair 0 comma 0. Here we get the ordered pair 1 comma negative 1. Here we get the ordered pair 2 comma 0. Here we get the ordered pair 3 comma 9. And from here we get the ordered pair 4 comma positive 32. Okay, so we start to graph all of these points. These and many others, when we graph them, begin to give us an idea of what the graph looks like. So I'm going to use Desmos now to do a better job of continuing this process. So let's define our function. F of x equals 2x to the third power minus 2x to the second power. Okay, and let's, well, I guess I kind of ruined the punchline there, but let's begin by creating a table of values. So let's get rid of this thing as an x. Let's make this this equation. Okay, so let's create that same table I had before. Let's start with, say, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5. Okay, so here's the exact same table that I hand wrote. Here are the input values. They go into this function in here. They get, each one of these values gets cubed and subtracted minus twice that same value squared. And so we get all these ordered pairs. And we can begin to graph them all. That's what these individual dots are here. Maybe they're a little hard to see with the purple. Let's change the color. Let's make them blue. A little better, maybe? Okay. Okay, so here they are, and I can spot them. So here's negative 1 comma negative 3. That's this ordered pair. And then 0 comma 0 is on there as well. And then 1 comma negative 1 is on there. And then 2 comma 0 is on there. You notice they grow pretty quickly, and the output values get pretty large, and the scale here only goes up to 8. So if I wanted to zoom out, I can spot some of the other ones. Here is 3 comma 9. Way down here is negative 2 comma 16. Okay, now the nice thing about this technology is I don't have to stick to simple whole numbers. I can put in some decimals as well. So if I evaluated that function at 1.2, I can get an output, right? And that would be over here, 1.2 comma negative 1.152. So it's pretty easy to just come up with several of the values that can help me fill out this table. So maybe 0.2, maybe 0.7, maybe 0.3, maybe 1.5, 1.8, right? Maybe 2.1, 2.3. About a few of those negative values, negative 0.2, negative 0.4, negative 0.6, right? And so we can see that we're slowly starting to put together an idea of what this thing would look like. And of course, the more points you put, the better the image becomes. Negative 1.2, negative 1.2, negative 1.7. Okay, so we slowly start to see what this graph would look like. And then, of course, now we can just graph the equation. And so let's put it in blue. Eventually, all those dots begin to form the actual graph of our function, right? So usually we just look at it like that and go, okay, here's the graph of the equation. But instead of a solid curve, we should really think of it as an infinite number of ordered pairs, so that together they begin to form that shape, the graph, which represents this equation. Okay, so after all that work, we have ourselves the original function. But this question wasn't about graphing functions. It was about how to transform them by adding or subtracting constants. So let's look at that. Okay, so finally we have the graph of our equation. Let's go back over here. And let's look at what happens to our function as we add, say, a 3. So let's say we have now a new function, g of x, which is defined to be equal to f of x plus 3. Okay, all right, so now we can again create a table of values, x, and now this new function, g of x, new function g of x. And again, let's just type in some easy values. So if we try typing in x equals to 0, then g of 0 is going to be equal to g of 0, come on, g of 0, g of 0 equals to f of 0, plus 3. And f of 0 was 0, right, over here. If we go back to f of 0 led to a 0. So this is going to be equal to 0 plus 3. So it's just going to give me a value of 3. Good. Okay, so if I try other values, let's say we skip down here to 3. We let x equal to 3, then this would be g of 3, which equals to f of 3 plus 3. And f of 3, well, that comes as a result of plugging in 3 into the f function, which gives us a 9, 27 minus 18. So this is going to be 9 plus 3, which is going to be equal to 9 plus 3, which equals to 12. Good. Okay, well, obviously, what happens is whenever we evaluate the g function at any input value, we're going to get the same output value as f, but then we add 3. So it makes sense that we can just kind of skip some of those middle steps there and just add 3 to this output. Right? So when x equals to 1, I know the f function is going to be negative 1 plus 3. So this is going to be equal to 2. Negative 1 plus 3 equals to 2. And then the 2 leads to a 0, so it's just going to be a 0 plus 3. It's going to be 3. Over in the negative values, negative 1 leads to negative 3 plus 3, which leads me to 0. Negative 2 leads to negative 16 plus 3, which equals to negative 13. Okay, so at every point along the input values, we get the same output value as before, plus 3. Okay, so now let's explore what happens to the picture, the graph, when we do that. Okay, so let's go back over here. Let's begin with the ordered pairs. So let's look at Control copy. Control E. Plus 3. Okay, that's going to be there. So let's come up with a new function, g of x, which is equal to f of x plus 3. Okay, so now let's start putting in some points. 0, comma, f of 0. Okay, that's good. Let's do this. So here were the ordered pairs that we got for the original function, right? We started to graph a bunch of these ordered values for the original function f of x, and then after putting in a bunch of these, maybe we were convinced that if we kept going, coming up with individual ordered pairs, eventually the graph would look like that, right? So that was the original function. Now let's look at these kind of on a point-by-point basis. So let's look at an individual point on here. Let me zoom in a little bit. Let's look at the number 1. The number 1 in the original function traveled to 1, f of 1, 1, comma, f of 1. And it was this guy right here, right? For the original function, when we evaluated this guy, we ended up with 1, comma, f of 1. Let's label it over here. About in 3, comma, negative 2, let's label let's label y okay, so let's label this guy here with this. Control copy. Come down here. Equals Control B. It's going to give us that. That's not what I want. Damn, we'll put it in blue. Okay, so now let's explore what happens as we evaluate the new function, g of x, equal to the old function, f of x plus 3, at the exact same point of 1. So let's find that. So at 1, we end up with 1, comma, g of 1. Label it. And notice what happens. So the old function, 1, mapped to negative 1. But now for the new function, we add 3. So the new value comes up here to this dot value here. And let's put it in red. red. There we go. Okay, so it went from being below to -1, being up to +2. So it went up by 3 points. And we can do the same thing with a couple of other ones. Copy, Control V. How about at 0? So at 0, the old function was mapped to 0, 0, but now the new function is going to map to 0, 3. Okay. Same thing happens with other points. Let's try maybe one more. Control V. How about -1? At -1, the old function, the original function, -1 maps to -3. Sorry, I had to catch it there. One maps to -3, but now the new function is going to map it to 0, right? So at every point on a point-by-point basis, this little gap here is a distance of 3 units up. Okay, so if we do it for a lot of points, let's go back over here. We can just do that for all these points. And let's put them all in red. See, on a point-by-point basis, we start to see that every point in my new function is going to be exactly 3 units higher than the old one. And so, let's zoom out a little bit. We see that eventually, as we graph more and more of these points, we start to see that the new function is equivalent to the old function, but shifted up, right? It's the same shape, but the whole thing gets shifted up by 3 units. So that's what happens when you add 3 to the original function. You shift it up by 3 units. Okay, nothing special about the actual number 3. So let's look what happens as we add or subtract different values. Okay, so here we have a case where it's the original function is the blue one, and then we add 3. So we can also add 2 instead, and we get that. Or we can add 5 instead, and it's off the screen there, and that's because it went up high, so we have to zoom out. So there it is at +3. Also, if in fact we subtract the constant, like say -1, then we go below. The exact same graph gets shifted down by 1 unit, or it can get shifted down by 2 units. Good. Okay, so let's create it as a slider. So we could say that it is +c, where c is a slider. And let's leave it as a 0 to begin with. So there's c, and we can label, let's label at 1, say at 4, 2. 4, 2, and we're going to label y equals x to the 3rd power minus 2x to the 2nd power. So there's my regular f of x. Well, actually, I guess I just put f of x. F of x. F of x plus, and this curly brackets and c, close curly brackets. There we go. Let's make it large. Large. There we go. Okay, so here is our value c. So it's equal there. Both graphs are the same. The red one is the f of x one. Let's change it to red and red. Okay, and as c goes up, as we add constant values, we get y equals f of x plus 0.6, plus 1.4, plus 1.8, plus 2.3, right? So it shifts it up. And then as we subtract, we go down, we see that it subtracts -3, minus -7, minus 3. Adding a -3.7, same thing as -3.7, and so on and so forth. Okay, so adding or subtracting a constant shifts the graph up and down. Okay, good. So then going back to our PowerPoint, right? That's what we just discovered right here. That if we have a graph f of x, and we want to think about what happens to the graph as we add or subtract a constant, it'll shift the graph up and down by that constant value. Good. Okay, so here's a nice little image of the same thing. If we have g of x equals to x squared plus 3, then we end up with a graph that looks like this red one. Remember, the blue one here is just your standard parabola x squared centered at 0, 0, but that plus 3 is going to shift it up a little bit. And then this purple one down here, this is x squared minus 2. It shifts it down. Good. So adding or subtracting a constant shifts the whole graph up and down by that constant. Okay, horizontal shifts. Now let's consider what happens when we have a function f of x, and now we adjust it by coming up with a new function, which is equivalent to, say, g of x equals to f of x plus c. So the difference being that here the adding or subtracting of a constant happens inside the function, inside the argument of the function, rather than on the outside. And we want to know, how does that affect our graph? Good. Okay, so again, let's just explore it a little bit by hand, and then we'll go over to Desmos and see how that gets affected. Okay, so again, let's go back to our general function defined as f of x equals to x to the third power minus 2x to the second power. Good. We already had a table of values for that from before, so let's just write some of those down. Okay, so 0 was super easy. That was just going to be 0 cubed minus 2 times 0 squared. That was just going to be 0. Let's see, 1 was going to be 1 cubed minus 2 times 1 squared, which is equal to negative 1. And then let's skip 2. Let's do 3. So 3 cubed minus 2 times 3 squared. That was equal to 9. 27 minus 18, 9. And then we had a value for 2. We had a value for negative 1, negative 2, negative 3. So I'm not going to redo all of those. I'm just going to copy them and let me get them. So we had negative 3 mapped to negative 45, and negative 2 mapped to negative 16, and negative 1 mapped to negative 3, and 2 mapped to 0. Okay, so here was the original function. What we want to do now is think about what happens with this new function. And the new function, let's consider it as, and let's put a different color on here to really pop out. My new function is going to be g of x. My new function, well, I don't want to do that. Let's say my new function is y equals to new function f of, and then the function, let's say we add a 3, x plus 3. Let's make it smaller. Let's make x plus 1. Okay, what's that going to do? Well, this is a new function, so we could also label it as a new function g of x equals to g of x, which is equal to f of x plus 1. Okay, so now let's create a little table value to see what this is. We have x, and then we have this new function g of x equal to f of x plus 1. Okay, so when we type in a 0 into this new function, what we're going to do is we're going to evaluate the f function at x plus 1. That's what's going to happen here. So this is the same thing as f of 0 plus 1, 0 plus 1, which is the same thing as f of 1. Good. Okay. Which, well, f of 1, that's going to be 1 cubed minus 2 times 1 squared, which is 1 minus 2. That's going to be negative 1. Good. Okay, when we type in, say, 2, 3, let's go to 2. When we type in a 2, then this is going to be 2 in there, and this is going to be the same thing as, f of 2 plus 1, which is the same thing as f of 3, and this is going to be equal to 3 cubed minus 2 times 3 squared, which gives us 27 minus 18, which gives us 9. Okay, so I could do this little equation, or once I get to this point here, then I can just go over to my table and look up 3 and note that, oh, okay, this is going to be 9. Good. And when I type in different values, so let's say I try putting in a 1 here, I know that this is going to be f of 1 plus 1, f of 1 plus 1, so I know that this is going to be f of 2. F of 2. So again, I can plug it into my equation and figure it all out, or I can go over to my table over here and see that the answer is going to be 0. Right? So when I want to evaluate the number 3 in here, then I know that the answer is going to be the result over here in 4, right? Because it's plus 1. And when I want to evaluate -1, I know that I'd have to look at this table and find the value at 0. So I know that this is 0. And at -2, I know that this is going to be the same as the answer of f of -1, so I know this is going to be -3. And then before that, it's going to be -3 leads to -16. -16. And -4 is going to lead to -45. Okay, so the pattern we see, hopefully, is that we get all the same outputs, the same sort of sequence of outputs, -45, -45, -16, -16, -3, -3, 0, 0, right? -1, -1. So we get all the same outputs for the sort of similar set of inputs. They've just been shifted a little bit, right? 0 mapped to 0, but now -1 maps to 0. And then -1 mapped to -3, now -1 maps to 0, right? So the same outputs, but they've just been shifted a little bit. Good? Okay, so that's different than saying f of x plus 1, right? Note that before we were working with something that might look like this. Come on. F of x plus 1, right? F of x plus 1, this just shifts this function up by 1 unit. Whereas here we're not getting outputs that are bigger by 1. We're getting all the exact same outputs. They've just been shifted here. There's been a shift of 1 in this direction. The inputs get shifted by 1. Good. Okay, so now let's explore what that does to our graph using Desmos. So back to this guy, and let's get rid of some of these things. Okay, well, let me put this in general over here. So this guy right here, let's just change it to a case of this. What if I had g of x equal to, I don't want to do that. Let's go here. So let's explore what happens to my function as I add plus 1. That's what we want to do. So if we do it on a point-by-point basis, let's put in here, let's trap these guys in here. Okay, so now we have the equation I want. Let's see if we can. Looks like there's no way to stretch this out. Anyway, okay, so this is x plus 1 cubed minus 2x plus 1. It looks like this. G of x, equals f of x plus 1. So it's the same thing as saying it's x plus 1 power of 3 minus 2 times x plus 1 to the power of 2. Good. So this is f of x plus 1. We're plugging in x plus 1 into each one of these x values and getting this as a result. So that's what I was typing into Desmos, what I typed into Desmos. And let's explore what happens on a point-by-point basis. So let's get rid of so many points here. Okay, so 0 looks like this. So 0 originally mapped to 0. We're happy with that. Here's the original function. But now when we put in plus 1, we end up getting this value here. Okay, so that initially might look like what we did is move it down, but that's not what happened. What happened was that when we typed in 0, we really got the answer that we normally would have gotten when we typed in a 1 here, right? Because 0 plus 1 is 1, and the output of 1 is -1. So that's why this -1 ended up being the result of that one. Good, so let's keep going and seeing the pattern. So when we type in a 2, originally 2 mapped to 0, 2 mapped to 0, but now we're really going to get the values that we get when we type in a 3, which is where that 9 comes in. Good. Let me just do a few more, and we'll hopefully start to see the pattern appear in the graph a little bit better. Okay, so these are going way, way out of control out of the graph, right? So those are poor choices. Let's go back to some nice, pretty decimal values. How about 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1.1, 1.2, 1.3. How about negative 0.1, negative 0.2, negative 0.3, negative 0.4, negative 0.5, negative 1.1, negative 1.2, negative 1.3, negative 1.4. Okay, and so on and so forth. Okay, so we start to see what happens to the graph of this after we continue to pump in lots and lots and lots of points. Eventually, we start to see that it begins to look like this. Good. So the original function was this one, and why is this labeled? So this is going to be f of plus 1. There. The original function in blue is f of x, and then plus 1 is this one. It's been shifted. Now, a little counterintuitive, you would think it's shifted to the right because it's plus 1, but really it's been shifted to the left by 1 unit. Each 1 unit has been pushed back because when we're evaluating this point at negative 1, we're really going to get the same value we would have gotten here at 0. When we're evaluating the original function, sorry, the new function at 0, we're really going to get the result we normally would have gotten when the original function was at 1. Right, so everything has been shifted back by 1 unit. Good. And again, there's nothing special about 1, so we can make it a constant. So let's go back to make this a 0. Make this a c. And then let's label this guy as plus c. There we go. Okay, so when we add 0, we get to the original function. And let's get rid of those guys and get rid of those guys. And then as we shift this, right, as we add values, so here is the original function of f of x. I want to label that. Let's label that at the point 4 comma 3. So the original function is f of x, right? F of x was defined here, x cubed minus 2x squared. So that's the blue function. And then the g function is equal to f of x plus a constant, where that constant at the moment is 0.4, and you see how it's been shifted to the left by 0.4, shifted to the left by 0.5, by 0.6, by 0.7, right? So the more we add there, the more it shifts to the left, right? Notice that the exact same picture is retained, the same image, the same curvature, it's just been shifted to the left. And likewise, we can also add a negative, so that looks a little funky. How about if we put it in parentheses? So we can add a negative value, so plus a negative 0.1, plus a negative 0.7, 0.8, and it shifts it to the right. Right? Again, a little counterintuitive. You would think that if you're subtracting, you'd go that way, but it's the opposite. So keep that in mind. Okay? So that's how adding or subtracting a constant works when we're adding it inside the argument of the function. And then, again, comparing it to the previous one, where we had, I don't know, let's say h of x, oops, h of x equal to f of x plus a constant, right? So when we had h of x equal to f of x, the original function plus a constant with the plus a constant at the end of the function, on the outside of the argument of the function, it would shift it up and down, right? On the other hand, if we are adding a constant inside the argument of the function, then that would mean that we are shifting it left and right. Good? Left and right versus up and down, depending on whether we're adding the constant inside the argument of the function on the outside of the argument of the function. Good. Cool. All right. Hopefully that made it good. Okay. Back to this guy then. All right. So then the general rule says that if we have some function f of x and we're adding or subtracting a constant inside the argument of the function, then we're going to be shifting the function left and right. Right? Left and right. Depending on whether we're adding or subtracting. And it's a little counterintuitive. When we subtract a constant that's positive, we're really going to go to the right. And when we subtract a constant that's negative, we're really going to be, when we subtract a constant that's positive, so say like minus 3, then we're really going to the right. And when we add a constant that's positive, then we're really going to be going to the left. So here's some more examples. So say we have our standard parabola, x squared, and then we want to consider what happens when we have x plus 4 in parentheses squared. So this plus 4, what does this plus 4 do? So again, it's a little counterintuitive. It goes to the left, right? So it's going to be the regular parabola shifted to the left by 4 units. And this one's going to be the standard parabola shifted to the right by 2 units. Good, so here's a nice image of that. Here is our standard parabola, x squared. And this one is the standard parabola shifted to the left by 4 units, whereas this one is the standard parabola shifted to the right by 2 units. Good. Okay, now reflections. So suppose that we want to look at what happens when we multiply a standard function by -1 as compared to evaluating the function at negative x. So whenever we see negative f of x or f of negative x, remember we can always expand this into thinking that, of this as a -1 times f of x. And this one we can always consider it as f of negative x. Good. Okay, so let's again go back to our little equation and let's see what happens. So if we had f of x equal to x cubed minus 2x squared, and we had our nice little table of values. I'm not going to go through those evaluations again. I'm just going to put them down. F of x, and let's say we had -3, -2, -1, 0, 1, 2, 3, and so on and so forth. That's good enough. -3 mapped to -3, -2 mapped to -16, -3 mapped to -45, 0 mapped to 0, 1 mapped to -1, 2 mapped to 0, and 3 mapped to 9. Okay, so here was the original ones. Sometimes the input is negative and the output is negative. Sometimes the input is positive and the output is negative. And sometimes the input is positive and the output is positive, right? So here's the original function. And now we want to explore what happens to this new function. The new function, let's say it's called g of x. And g of x is equal to -1 times f of x, where the -1 is definitely on the outside of the function, right? So how does that affect the graph of our new function? Well, if we create table values, right, again, we can have the same ones, -3, -2, -1, 0, 1, 2, 3. Okay, so at, say, -3, the new function g of -3 is equal to -1 times f of -3. So this is saying find the value of -3 from the original function, which was -45, and multiply it by -1. So obviously, I'm going to get a +45. Good. At 2, okay, so this is going to be g of 2, the answer to this new function. Well, that's going to be equal to -1 times f of 2, which is going to be -1 times the value of f of 2, which was 0. Okay, that's just going to give me 0. At 3, g of 3 is equal to -1 times f of 3, which equals to -1 times 9, which equals to -9. Okay, I don't think it takes long to realize that what's happening here is that we're always going to take the output from the original function and multiply by -1, which means we're going to get the opposite sign. So at -2, I know that this answer is just going to be +16. Come on, +16, right? Because that was negative. And at -1, this is going to be +3. 0 stays with 0. At 1, instead of getting a -1, I'm going to get a +1. 0 stays with 0. And then instead of +9, I get -9. So all we're doing is taking all previously positive outputs. It used to be positive. And now we switch it over, and we're going to end up getting a negative. Previously positive answers become negative. And then previously negative outputs are now all going to become positive outputs. And then 0 stays with 0. 0, still a 0. With a 0. Okay, 0 stays with 0. Previously negative become positive, previously positive become negative. How does that affect the graph? Okay, so let's go back over here, back to Desmos. Let's not label that guy. Okay, so we have our function f of x as defined up here. F of x equals to x cubed minus 2x. Okay, so this new function, which we're going to define as g of x equals to negative 1 times f of x, this new function. Okay, so we established that what happens with this new function is that whenever we plug in the same input to both functions, the signs of the outputs get swapped. So previously positive, anything above the x-axis was a positive output, becomes a negative output. And previously negative outputs, that's these ones below the x-axis, become positive. Okay, so let's graph that and see what happens. It looks like that. Right, so this section of the original graph in blue is, let's change this thing over here. Negative 1 times that. Okay, so here we go. So the original function here in blue, as compared to the new function, which is negative f of x, right? It's a reflection about the x-axis. Make this smaller. I don't need to make that bigger anymore. It's a reflection about the x-axis, right? It's a mirror image about the x-axis. All previously positive answers in the original function become negative. All previously negative answers under the original function become positive, and so on and so forth for these various sections. Okay, good. So having this minus 1 becomes a reflection about the x-axis for any function. Right, so that's what this part of the statement is saying. If we have y equals to negative f of x, then we're going to get this kind of a thing. Here's f of x, and then negative f of x is going to be a mirror image reflection across the x-axis. Right, reflect y equals to f of x across the x-axis. On the other hand, the other one we want to consider is what happens when we multiply the argument of the function by a negative 1. Right, that's different. The negative 1 is on the inside of the function. So let's explore what happens with that case. So again, back to our good old trusty f of x equals to x to the third power minus 2x squared. And we have our table values. So we had negative 3, negative 2, negative 1, 0, 1, 2, 3, something like that. Okay, and we had our values of negative 45, negative 16, negative 3, 0 still mapped to 0, 1 maps to negative 1, 2 mapped to 0, and 3 mapped to 9. Okay, so here is our original function once again. But now we want to explore what happens to this new function. Let's call it h of x. This new function, h of x, which is going to be equivalent to the old function, but we multiply the input by negative 1 times x. Good. So now when we come up with this new table of values for this new function, so we can figure out what it looks like, this new function, h of x. Okay, so we're going to type in some values, negative 3, negative 2, negative 1, 0, 1, 2, and 3. Okay, so when we type in a negative 3, we want to figure out what is this graph evaluated at negative 3. Well, the instructions are that it's equal to the old function where there's a negative 1 in here, negative 1 times the new input value of negative 3, which then just becomes f of 3. Okay, and then I could just plug in the 3 into this equation, 3 cubed minus 2 times 3 squared, or I can just look at my old table values and see that 3 maps to 9. So at this point, I can just take the shortcut of saying that equals to 9. And same thing with the others. H of negative 2 equals to f of times negative 2, right? So there's a negative 1 here. And now negative 1 times negative 2 equals to positive 2. F of 2. Which means I can go back to my table and see that the answer is 0. Okay, so we start to see a pattern here. When I plug in a -1, I'm really going to get the answer I normally would have gotten for f of +1. So here I can see that this is just going to be a -1, the result from there. And 0 is going to be the result. Well, you multiply by -1, you still get 0. So 0 still gives you the same answer as 0, right? The same output as 0. 1 is going to give you the same output that you normally got under -1. So then this is going to be equal to -3. And 2 gives you the same answer as -2. And it's -16. And 3 gives you the same answer as -3, so that's going to be -45. So the pattern we notice is that there's a swapperoo here with the output values as they relate to the input values. When we plug in 1, 2, 3, 4, we're going to get the same answers as we previously got from -1, -2, -3. When we plug in -3, -2, -1, we're going to get the same answers as its positive counterpart of 3, 2, 1, right? So there's going to be a switching that happens. So let's look at these in terms of ordered pairs. In terms of ordered pairs, the original function had 3, -45. The original function had -2, comma, -2, -2, -2, comma, -16, -16. The original function had 3, 3, 3, comma 9, and let's say the original function had, man, this computer really fighting me, 1, comma, -1. Okay, so these are the ordered pairs from the original function, and let's see how they compare to this new function where we've multiplied the argument of the function by -1. So now they map to -3 maps to 9, where we used to have +3, comma 9, now we have -3, comma 9. And then 2 maps to 0, that's not boring. How about this one? So then 3 maps to -45. Where we used to have -3 maps to -45, now we have +3 maps to -45. And then 2 maps to -16, where we used to have -2 maps to -16, now it's +2 maps to -16. Okay, so let's see how this pattern affects our graph. So let's go back to our good old trusty Desmos, and let's turn that guy off, and let's turn off this guy. Okay, so here's our original function that we've been working with, and the function is right there. Okay, so now we want to define a new function. Let's call it h of x, which is equivalent to the old function, but we multiply this by -1 times x. Okay, so let's just graph it, okay, and explore what happens. What is this? So what's happening is that the old value, the old function, let's find some of these points. The original function had some of these key points. These are all points on the original function. In fact, let's see if we can graph a few of them. Here's a lot of them. Here's a bunch of points on the original function. I'm not sure why it's not letting me click on them, but here's all these points on the original function. And so what's going to happen to this point when I apply it to my new function? My new function is going to say that this is going to be, when I plug in 1.3 into my new function is going to give me the result I would have gotten before at -1.3, which is somewhere over here. There. Good. And here, when I go to my function to evaluate -2, it multiplies the -2 by a -1 to give me a +2. So the output is 0 because the original function evaluated at 2 was a 0. Good. So there is a switching that goes back and forth along this direction. Left and right, left and right, left and right. Right? The value for -3, the answer is going to be the same answer I would have gotten with +3 in the original function. So this value switches over here to give me the output of -3. Good. And when I want to evaluate my new function at 1, the output I'm going to get at 1 is the same old output I would have gotten at -1. So this one goes that way. Good. So there's a left and right switching that happens, and therefore it's a reflection around the y-axis. Good. Okay, so let's go back to this guy. So when there's a -1 inside the argument of the function, there's going to be a reflection across the y-axis. There's a swaparoo of the output values as we input different values of x. A positive x value gives me the result of the -1. I hope that made sense. Okay, so moving on then. Here's an example. So how does this compare? We have f of x equals to -f of x. Compare that, or also compare that to the original function. So -f of x, we take the original f of x, y equals to x squared function, which is a standard parabola centered at the origin of the graph, 0, 0. And then the fact that we have a -1 on the outside of the parentheses, so really we could write this as -1 times x squared, and it would be a reflection about the x-axis. So this point here, A, travels down here under the impression of the new one, A bar. And a point over here, B, travels down here under B bar, right? So there's a swaparoo across the x-axis that happens. Good. Compared to this one is similar to the square root of x, except instead of square root of x, we have square root of -x. So this is what we get. The original function, square root of x, is this blue one, and square root of -x is going to be this red one. So here what happens is that there's a swaparoo around the y. This point here gets shifted over to a point over here, A bar, and a point over there, B, gets shifted over in this direction to become a point across, a mirror image across the y-axis, so it becomes like that one, Y bar, under the influence of G. Good. So this is a mirror image reflection across the y-axis. Questions, questions, questions? Okay. Vertical stretching and shrinking. So now we just want to consider what happens when we multiply, two more I guess, when we multiply the outside of the function by a constant. So if we take every single value of our function and multiply it by a constant, let's see what happens. Again, let me go back to Desmos then. Here is back to our standard parabola, and we know that if we keep going, eventually we graph all of those guys that will look like that. So now we want to explore what happens when we multiply a constant times that. So let's say we multiply it by 2. What's going to happen to that? So on a point-by-point basis, there. So if we multiply everything by 2, then we're just doubling all our values. So they'll look like this. Now notice that 0 stays at 0, and then 1 multiplied by 2 becomes 2. 4 multiplied by 2 becomes 8. So we have our original parabola value there. And look what's happening with all these new values that are the result of multiplying by 2. We're just doubling everything, so we're going to stretch. I'm going to stretch the whole thing vertically. It's going to go toward infinity faster. Right? It's going to go up toward infinity faster. So the new graph is going to look like this. X squared equals to 2x squared. It's going to look like that. Okay. So as we multiply by bigger and bigger and bigger numbers, then it's just going to get stretched out. It's going to go toward infinity faster and faster and faster. Right? The skinnier it gets. The bigger that number is, the skinnier it gets. It can get ridiculously big. 18. How about 28? It's skinnier and skinnier and skinnier. So in general, if we just leave some constant there, then the bigger that value we multiply by a number that's bigger and bigger and bigger, it's skinnier and skinnier and skinnier and skinnier. Okay. On the other hand, what if that number was a decimal between 0 and 1? If it's a decimal between 0 and 1, then it's going to kind of slow down its growth. Right? Let's go back to the way these were being described. Let's put that in there. So if we go back to the squares, now instead of doubling all your outputs, multiplying them by 2, if you multiply them by 0.5, then you're halving all of them. You're slowing down their growth. They're still going to go toward infinity, but just at a much slower pace. So you end up with these purple dots. Right? Instead of 1 mapping to 1, it'll map to a half. Instead of 2 mapping to 4, it'll map to 2. Instead of 2 mapping to 16, it'll map to 8, right? Because you're halving all of your output values. You're slowing down its growth. So what you end up getting is a parabola. Y equals to 0.5x to the second power. A parabola that's a little wider than the original one. Good. So let's change this from 0 to 5.2. Yes. Okay. So in general, if we are if we're going to be multiplying by a constant that is bigger than 1, it makes it skinnier and skinnier and skinnier. The bigger that number, the skinnier it gets. When we multiply by 1, of course, then we just get the original function. Is 1. And then if we multiply by a decimal that is smaller than 1, between 0 and 1, then it gets wider and wider and wider and wider and wider until we multiply by 0, which gives us the horizontal axis value. Good. Any questions about that? Wider and wider. Okay, and then of course if then b becomes negative, then we also have a reflection about the x-axis. So this can go from negative 5 by 2. Okay, so if we multiply by a constant bigger than 1, it gets skinnier. And then we can equal to 1, and we get the exact same function. Okay. And then if we multiply by a value between 0 and 1, it gets wider and wider and wider until we get to 0. And then if we continue and multiply by a negative number, then we end up getting a reflection about the x-axis. So that's the way it changes based on whether the constant you're multiplying is a constant bigger than 1, a value between 0 and 1, or whether it's a negative. More questions, more questions, more questions? A good way to look at this thing is, say, sine and cosine functions. Let's see if I have y equals to so here's a nice cosine function. I know we haven't gotten to trig yet, but I'm sure you've all seen cosine functions. So here's a nice cosine function. And let's explore what happens when we multiply a cosine function equals to, say, 2 cosine of x. So it's getting vertically stretched. Instead of having heights of 1, they now go up to a height of 2. And instead of going down to a negative 1, it goes all the way down to negative 2. Right? So it's getting stretched vertically by multiplying it by 2. You can multiply it by 3, and it'll just stretch it even more. Multiply it by 5, it'll stretch it even more. On the other hand, if we multiply it by a decimal that's between 0 and 1, like 0.5, then it flattens it out, right? It compresses it. The original one of cosine is the red one, and now 0.5 cosine is going to be this blue one that gets squashed down. And the smaller the decimal, the more you squish it down. It's 0.2 cosine of x, right? You compress it compress it vertically. 0.1 gets compressed even more. Good. But notice that the zeros never get affected. It still goes through that point, still goes through that point. The only thing that gets affected is all the other output values. Any questions? So if you put a b in front here and just check it for different values of b. So when b is bigger than 1, then it stretches it in both directions, stretches it vertically. When b equals to exactly 1, it's equal to the original function. When b is a value between 0 and 1, it'll compress it, compress it, compress it, compress it until it gets to 0. And then when b is a negative, it'll be a reflection about the x-axis. So it'll start to flip it over. So this point there moved all the way down here, became a reflection, and got compressed until we get to negative 1. So here is a perfect reflection about the x-axis. This point moves down here. This point moves down here. This point moved up to there. Okay, good. And then if we go even deeper into the negatives, and we continue to stretch it this way. Okay, so here's the value of b moving around. Any questions about this? No, sort of, kind of, maybe. Okay, so we want to say that if we multiply on the outside of the function by a constant that's bigger than 1, then we stretch it stretch it vertically. So the original function is the blue one. The new function is this red one when c is bigger than 1. When c is a value between 0 and 1, we compress it vertically. So the original one is the blue one, and then the new one, when we multiply by a decimal, is going to be this red one. No questions? No questions? Okay. So let's consider these guys. If we want to do a rough sketch, get a rough idea of what these graphs look like, this first one, g of x equals to 3x squared, is going to be like the x squared function. But the fact that we have a 3 in front here means that we're going to stretch it vertically. It's going to get skinnier. It's like a skinnier version of a parabola, skinnier compared to the standard x squared function, because it's going toward infinity faster, right? All the outputs get tripled, so you're going to get to infinity faster. When we multiply it by a third, we're slowing down its growth, right? So all the outputs get multiplied by 0.33. So it's still going to go toward infinity. It's just going to take it longer to get there. So as compared to the original x squared function, this is going to be a much flatter curve. Good. So we played with those already. The original one is the purple one. The red one is 3x squared, so it's skinnier, going toward infinity faster. And the 1/3 x squared is going to be this wider blue one, right? It's growing more slowly. But they all go through the point 0, 0. Good. Last one, horizontal stretching and shrinking. So now we want to consider what happens when we multiply the function on the inside by a constant. And again, we want to think about what happens when that constant is positive, negative. What if that constant is bigger than 1? What if that constant is a decimal between 0 and 1? We want to consider what happens to those. And again, we're going to use Desmos to consider those. So let's stick to the cosine function. So we know that if we multiply by a constant on the outside of the function, we're going to stretch it. Vertically. But what happens if we multiply by some constant on the inside of the function? So let's look at y equals to cosine of. Let's make it 2x. Okay, let's explore what happens. The original one is cosine 2x, so here is one period of cosine in red, starting from there all the way out to there. This is in radians, so it's in 2 pi. Remember, 2 pi is a little bit past 6. 1 pi is 3.14, so this is about 6.2 something. Okay, so the red one that represents one period of cosine, but now the green one is cosine 2x. So what we're doing on a point-by-point basis is that we're doubling all our input values. So if I'm inputting angles, but the first thing is I double the angle, then I find the cosine, then I will experience every single value of cosine in half the angles. By the time I go from 0 to pi, I will have already experienced all the output values of cosine one time. So that's why the entire period of one cosine gets drawn out in the space, in half the space. Right? In degrees, normally a cosine takes from 0 to 360 degrees, but if I just evaluate it from 0 to 180 degrees, I will have experienced every single value of cosine one time. Right? So the period gets compressed, which is, again, maybe counterintuitive. You think that because you put a 2, it might not be intuitive, that what you're doing is compressing it. You're making it go faster. Right? When you put a 2 there, you make it go twice as fast. And if we put a 3 there, well, then we make it go 3 times as fast. So in the gap between 1 and 2 pi over 3, so in the space in degrees, normally would take between 0 and 360 degrees. This red one is one period of cosine. But now, because we're tripling every single angle, I plug in a 0 angles. I plug in 10 degrees, 30 degrees, 50 degrees. As I plug in different values here, different angles, I triple them. So by the time I go to 120 degrees, because I'm tripling everything, I will have already experienced every single value of one period of cosine, right? And then sticking to radians, then as I stick in half a pi and pi over 3 and pi over 5 and 2 pi over 3, right? As I plug in different values of pi, then as I plug in values between 0 and 2 pi over 3, I will have already experienced every single value of the cosine function one time. So I've made the period go faster by a factor of 3, which means that I can squeeze in 1, 2, 3 complete periods of cosine in the same space where I normally would have only fit one period of cosine, right? So I've made it go faster and faster and faster. The bigger this number is, the faster it'll oscillate. So now I'm squeezing in 5 complete periods of cosine in the space where I normally squeezed in 1, or even faster, I can do 10 of them. 10 different cosines, right? So these little green ones oscillate back and forth 10 different times in the same space where the regular cosine function would have done only one. Good. By the same token, going in the other direction, if I multiply it by a decimal, like 0.5, then I'm slowing down its growth. As I'm plugging in different angle values, angle 0 degrees, angle 10 degrees, angle 50 degrees, because I'm multiplying everything by half, I'm only going to experience all the outputs in the same span of time where I normally would have gotten one complete period of cosine. I'm only going to experience half the results because I keep halving them all. So when I plug in 2 pi, I'm really only going to get the output of pi. When I plug in pi over 2, I'm really going to get pi over 4, right? So it's slowing down the oscillation period. If I want to see one complete period of cosine, now I'm going to have to go the other direction and zoom out, right? Where normally 2 complete periods of cosine would have happened between 0 and 4 pi, right? The red one is the original cosine function, right? I would have, it's going to take me 2 complete periods of the regular cosine to complete one period of this new cosine function that has a half in there, right? It's slowing down its growth. That's what happens when you multiply by a value between 0 and 1. And then, of course, we know that if we go into the negatives, we end up with a reflection about the y-axis. Good, 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 good. Okay, so if we put in a b in here, let's not put it over there. So if we just multiply by some random value b, so as b, when b is equal to 1, we get the exact same one. As b becomes bigger, right, this constant we're multiplying, as it becomes bigger, we see a horizontal compression, right? It goes through its period faster. It oscillates faster in the same space. As we plug in values that are between 0 and 1, it stretches it out. So you see here we have to go way out to see one period of cosine. Right? One period of cosine is all the way out there to there, from 0 to 10 pi to do one period of cosine, and that's where the b equals to 0.2. So this is cosine of 0.2x is this green one. And in that same space, we could have done 5 periods of the regular cosine. Any questions? No? No? Okay, going back to this thing then. So, horizontal shrinking and stretching of a graph. So if c is greater than 1, then f of cx is going to be related to f of x in that it is a horizontal compression, a shrinking. It goes through its period faster. So here is what it would look like. The original one is the blue one, multiplying it by cx, where c is a positive number greater than 1, then it makes it go through its period faster. On the other hand, if c is a value between 0 and 1, then the original function is in blue, and then multiplying it by c, multiplying the argument of the function by c, where c is between 0 and 1, is going to stretch it out this way. It's going to take it longer to go through its period. Any questions about that? Okay, so if we're given this graph right here, we don't necessarily know the equation of it, we just know its graph, we know its picture. What would it look like to have f of 2x? So we know that the fact that this is a number bigger than 1 makes it go through its period faster. So instead of completing one little oscillation, let's say it goes from 0 to 1, it completes one triangle, it should complete the whole thing in a half. Right? So that should be 1/2. It's going to complete it twice as fast because there's a 2 there. Good. And then it'll do another triangle in the same span of time there. So in the same span of time that normally did one triangle, now it's going to do 2 triangles. That's what that one is going to look like. So that's this one. So it looks like the same picture, except they just changed this thing here. So you'll just be able to do more of them. Good. And then for this one, well, it's slowing it down in half. So it's going to take twice as long to do one triangle. So where it normally did one triangle from 0 to 1, now it's going to go from 0 all the way out to there, and then all the way out to there. It's going to go out to 2, and get twice as long in order to complete one triangle, one period of its graph. So from there to there. All right, so I'm going to move this around a little bit and write it this way: -1/2 x minus 1 squared and then plus 3. And let's think about what happens with each one of these. So the minus 1 is going to be a shift in the horizontal direction. So it's going to move it left and right, the plus or minus. And in this case, minus 1, the new 0, comparing it to x squared, if you want to compare it to x squared is this parabola right here. But x minus 1 squared, the new 0 is going to happen when we plug in a 1. So it's going to get shifted to the right, like this, by 1 unit. Right, by 1 unit. Okay. What is this going to do? Well, the fact that it's a half means it's slowed down its growth, right? If we multiply it by a number bigger than 1, it makes it skinnier, it goes toward infinity faster. If we multiply it by negative 1/2, it's going to slow down its growth. So compared, that's going to be negative 1/2 minus 1 squared. That's going to be kind of like this one, except it's going to be wider. So maybe just to exaggerate a little, it's going to be more like that. And the fact that we're going to multiply by a negative means it gets flipped upside down. It's a reflection about the x-axis. So we're kind of slowly putting together what this thing is going to look like. So it's going to come down here. So there's negative 1/2 x minus 1 squared. And finally, putting the plus 3, we know that that shifts the whole thing up by 3. So my final guess at what this sketch graph is going to look like is something that looks like an upside down parabola that's really kind of wide, like this. Now this is just a rough sketch. I don't really know, important things to know is, okay, let's figure out what that is. Let's figure out what that is. Let's figure out what that is. Right, so all of these would be really nice, important points to figure out to get a really nice, detailed graph. But for now, all we want is just a rough idea of what this thing looks like. And it's going to be an upside-down parabola that's really wide. Good. To find these other things, okay, well, we'd have to find the y-intercept. That means we let x equal to 0. Plug in a 0, that becomes minus 1 squared is 1. That becomes negative 1/2 times 1. That's going to become 3 plus negative 1/2. That's going to be 2.5. Okay, so we should be able to get that this is 0, 2.5 fairly easily. This one's a little harder. We got to set this equal to 0 and solve for x, figure out the places where it crosses the x-axis. Good. Questions? No? Maybe? Okay, so for now we're just interested in kind of a rough sketch of the whole thing, and putting all these things together will help us do that. Okay, last concept in this section is to think about even and odd functions. So if function f satisfies that f of negative x equals to f of x for every number in x in its domain, then the function is called even. A classic example of an even function is x squared, where x squared, if we plug in a positive number, if we plug in a negative number, we always get the same result, right? So if we plug in, we use x so much that it looks a little confusing. So this is fine, or we could say f of negative a. I don't want to do that. So okay, so evaluating this function at a seems kind of silly. We're just letting x equal to a. So if we let x equal to a, then it's just going to be a squared, right? Of course, if we plug in a 2, then it's 2 squared. If we plug in a 3, we get 3 squared. But if we evaluate f of negative a, so we're letting x equal to negative a, then we're going to get negative a squared. And then that just equals to a squared, right? The negative 1 gets squared, so that just disappears. And so we're pointing out that we get the same answer. When you evaluate this at a or negative a, either way we get a squared. And so we get the statement that f of negative a equals f of a. Okay, well, they did the same thing here, except that they didn't introduce a new input value variable a. They just left it as x, and I think that ends up kind of confusing people a little since there's just so many x's running around. But that's what this is attempting to say, that if we evaluate our function at negative x and we evaluate our function at positive x, they both equal each other. Right? The fact that we inputted this extra negative in here made no difference. Good. Graphically, we could see that if we plugged in some number over here, a, and we also plugged in some number over here, negative a, that they both lead to the same output, right? They both have the same output value here of a squared. Good. So, as you can see then, it's going to be a nice mirror reflection about the y-axis. Even functions are a nice reflection about the y-axis, and they are even. Right? X squared is the most classic example of that. Cosine is also going to be even for that same reason. It's a nice reflection about the y-axis. Good. On the other hand, odd functions, if it's true that f of negative x equals to negative f of x for every number x in its domain, then f is called an odd function. And again, they did the same thing where they just evaluated the function at negative x. Negative x gives you negative x cubed, therefore we end up with negative f of x. So again, this looks a little messy, I think. If you like it, that's fine. I don't know, it's a preference thing, but doing the same thing as I did before, right? We want to evaluate this function. We want to let x equal negative a. Then we end up with f of negative a is negative a cubed, which gives you negative a cubed, right? Because negative 1 times, I'll do this, negative 1 cubed, just like the data there, which gives you negative a cubed, which is the same thing as negative 1 times f of a, because right? F of a is a cubed. F of a is a cubed. Good. So if we have the case where f of negative a equals to negative f of a, then we have something that's odd. Right? So any function that satisfies this condition, plugging in a negative a is equal to negative 1 times f of a, then you have yourself an odd function. And x cubed is the most classic example of that. Good, maybe. Another one is the sine function. So if we had g of x equals to the sine function, so let's say, okay. Let's say g of x equals to sine of x. As one individual example, let a equal to, let's say, pi, g of negative pi. And how does that compare to g of pi? Right? You want to see what happens, what's the relationship between these two. Okay, well, g of pi, that's going to be sine of pi. Oh wait, actually I don't want that. I want, say, pi over 2. Pi over 2, negative pi over 2. So sine of pi over 2, well, that's just going to give you a positive 1, right? And then when we evaluate sine of negative pi over 2, this gives you negative 1. So they're similar, except they're opposite signs. So in order to make them equal to each other, we introduce a new negative. Right? So we introduce this negative 1 times that, and now they equal each other. So that's true for any value. I just randomly picked x equals to this number, but then this is true. G of negative pi over 2 equals to negative 1 times positive pi over 2. And this relationship is going to be true for any value you choose for x. Any sine value, any angle you choose will give you the same result. When you graph them, this is what you get. So for an even function, it'll be a mirror image about the y-axis, whereas for an odd function, what you have to do is think about this, the line y equals to x. This line right here is the line y equals to x. Come on. Okay, thank you. this line right here is the line y equals to x. And so the graph is going to give you a reflection about this line. Okay. So how do we tell that a function is odd or even based on the equation? Well, all you have to do is follow those instructions and determine if it's true that f of x, if it's true that f of negative x equals to f of x, then we have an even case. Even. If it's true that f of negative x equals to negative 1 times f of x, then we have odd. And then if it's neither of those, then neither of those work. Then it's neither even nor odd. Good. So all we have to do is replace that x value with a negative. Now again, too many x's running around. Sometimes I think that gets a little confusing. So I'm just gonna replace it with a different value, say a. So I'm just gonna play with a. So I'm gonna say that f of negative a, and then that gets evaluated here. This is going to be equal to blank to the 5th power plus blank. And then that's going to be negative a. So negative a goes there, negative a goes there. Okay, and then I simplify. Whenever I take a negative number to the power of 5, because it's odd, we preserve its sign. So it's going to be equal to negative 1 times a to the 5th power plus negative 1 times a, gives you that. Now I can factor out that negative and do negative 1 times a to the 5th power plus a. And then this is exactly this original function evaluated at a. So this equals to negative 1 times f of a. This equals negative 1 times f of a. Good. So we've established that f of negative a equals negative 1 times f of a. So we've established that this function is odd. Good. Questions, questions, questions? Doing it for this one, let's do g of blank equals to 1 minus blank to the power of 4. And so we want to plug in negative a and see what happens. Well, we simplify it, and that's just going to be 1 minus negative a to the power of 4 is going to become positive, so this just becomes a to the power of 4. And then this is exactly this function evaluated at a. This is equal to g of a. Right, so we've established that g of negative a equals to exactly g of positive a. Therefore, it's even. Good. Questions, 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 questions? For this one, h of blank equals to 2 times blank minus blank times the power of 2. So again, we're going to replace the input variable x with a negative a, negative a, negative a. And we end up with negative 2a minus a squared minus a squared. Okay, and now if I factor out a minus 1, I end up with positive 2a plus a squared. And now, okay, well, this is not exactly this evaluated at a because of the minus. This has a plus, this has a minus. It's not equal to that. And so it's neither one. This one here before we factored out the 1 was not exactly equal to f of a. I'm sorry, h of a. So neither one of these is going to be helpful. So this one's neither. Any questions? Right? Not that one, not that one. Right? So this is not f of a, not f of a, and this is not negative f of a. Any questions? So the author did the same thing. So we replaced it with negative x instead of negative a, and then factored out a minus, and so we get negative f of x, so it's odd. And we got an even, and then we got an either. Okay, so then let's do a quick little recap then. So whenever you're given a question about whether this function is even or odd, you might be given a function, some function, f of x equals 2, and they might actually give you the equation, and it could be a polynomial, for example, 3x to the 7th power minus 2x plus 4, for example, just some random function, and they ask you, is this even / odd or neither? Question mark, how do we do it? From the equation. Okay, so what we have to do is input a negative x, evaluate the whole thing, and see if either we can simplify the new equation to be equal to exactly to the original one, or factor out a -1 and make it be equal to -1 times the original function. If you can do that, then you've established whether it's even or odd, and if it doesn't equal either one of them, then it's a neither. Personally, I like to use a different letter because we use x way too much, and I think it gets a little confusing, so I like to use a. So, if I have a, I have f of a, in this case, is 3 a to the 7th power minus 2 times a plus 4. So it's kind of a silly little thing where you just replace the x with all the a's, and it just kind of helps me visualize it a little bit. And now I want to consider this. So algebraically, if they give you the equation, you want to know, is this even, is it odd, or no? So what you're going to do is to evaluate your function at -a. Good. So you're going to come over here and say this is going to be 3 times blank power of 7 minus 2 times blank plus 4. And you replace all these values with -a. And now your goal is to use algebra to simplify this. Remember that whenever we have a negative raised to an even power, then that negative becomes positive, so we kind of eliminate the negative. Whenever we have a negative raised to an odd power, we preserve that negative, so we keep it. Okay, so sometimes you'll cancel out the negative, sometimes you won't. You'll end up with a new polynomial. Your goal is to see if that polynomial there ends up giving you exactly this one, right after a bunch of simplifications. Does it equal 3a to the 7th power minus 2a plus 4, which would mean then that it equaled f of a. Here would be a case where this would be a case where you plug in negative a, and the whole thing simplified to give you a. Or maybe the other case is that after a bunch of algebra, you simplify all of that, and maybe it ends up being equal to -1 times 3a to the 7th power minus 2a plus 4. Meaning it's all the opposite signs here, right? So it was equal to -3a to the 7th power plus 2a minus 4, like that. And then you factor out a -1 from all of these, and we end up getting 3a to the 7th minus 2a plus 4. If that's the case, then what we've established that this is the case of the thing simplifying to -1 times, and then this right here is f of a. Right? So if after you plug in a -a into whatever equation they give you, you use your awesome algebra skills and it simplifies to be the original function evaluated at a, you end up with an f of, this is the case of f of -a equals f of a. Right? This could be the case like this. And we know that in this case, this means that this is an even function. On the other hand, if you evaluate our function, the given function, at a -a, you plug it in, you evaluate it, you simplify, you use all those awesome algebra skills, and then you end up with something that's -1 times f of a. This is the case where we've established that f of -a is equal to -1 times f of +a. negative a equals to negative 1 times f of positive a. If that's true, you've established that this function is odd. Oops, I guess I'll leave it in the same pattern before. We've established in this case that the function is odd. Now you'll notice that if I actually do the algebra for this one, what do I get? I end up getting, okay, negative a to the power of 7 is going to be, we preserve the negative, so this is going to simplify to give me, negative 3a to the 7th power plus 2a plus 4. Good. And now if I factor out, well, okay, first of all, notice that this is not exactly equal to this one, right? It's close, but not quite there. It's off by signs. This one is positive 3a to the 7th. This one's negative 3a to the 7th. This one's minus 2a. This one's plus 2a. Okay, so it's definitely not equal to, this is not equal to f of a, right? So I've ruled out even. This definitely cannot be even. Not even. Okay, all right, so now I try the other possibility. I factor out a minus 1. Minus 1 times this whole thing. And I get a to the, I get positive 3a to the 7th power minus 2a minus 4. And we notice that this also does not equal to negative 1 times a, because this thing in here, this is also not equal to f of a. Again, we're very close. We have positive 3a to the 7th minus 2a, but here we have plus 4, and after factoring a minus, we end up with a minus 4. This is also not equal to, this is not negative 1 times f of a. So it's not odd. Not odd. So this is a case of neither. This equation is neither. Good? Okay, so whenever you get an equation, evaluate it at negative a and see if after simplifying it equals to f of a. After simplifying, does it equal to negative 1 times f of a? And if it doesn't equal either one, it's a neither. That's how you deal with it. A pattern that emerges with polynomial equations is that if you have a polynomial where all the exponents happen to be odd exponents, then you're going to find that your equation is odd. And if it's a polynomial with all the exponents are even powers, like 2s and 4s and 8s and 6s, then that will end up being an even polynomial, which is probably connected to why we call this phenomenon even versus odd with polynomials. But remember that we're going to be working with other kinds of equations that are not polynomials. And so the same rule applies. You just have to be a little bit more diligent about how you plug in your negative and how that gets either canceled or preserved. And again, with your algebra, does it simplify to the original function, or does it simplify to negative 1 times the original function, and be able to tell whether it's even or odd from that perspective. Now, graphically, how can we tell if the equation is not given to us? They just give us a graph, and they ask us, is this a graph of a function that's even? Is this the graph of a function that's odd? Okay, so let's take a look one more time at the description of an even function and an odd function. The even function is the easiest one. Let's look at that one first. So an even function is a case where f of x equals to f of negative x. Looks like this. Okay, so here is a classic example of what a graph would look like. Good. Okay, so remember from before that when we have a negative 1 inside the argument of the function, this is a reflection across the y-axis, right? So these two are equivalent to each other, saying that both graphs, the original graph and a graph reflected about the y-axis, are equal to each other. Right? That's what this is saying. Versus this one, the odd functions, this one is saying that, remember when we have a negative 1 on the outside of the function, this is a reflection about the x-axis. That's what this is saying. Here, let me write those down. So this is the original function. This is the original graph. Versus this one is saying that this is a reflection about the y-axis. Right? So if a function is even, it is true that that function and a graph, which is a reflection about the y-axis, equal each other. It means that when you do a mirror image rotation around a mirror image reflection across the y-axis, that both of those graphs are equal to each other. You can't tell that anything has happened. So notice that if we look at this classic example of an even function, If I rotate it about here, I rotate it this way, right? I do a reflection about the y-axis, you wouldn't notice that anything has happened, right? So a point here would be rotated to a point over here. So A, this point there would be rotated over here to A bar, and then a point here would be rotated over there to a point B. So this point B would be rotated to B bar, and the same in the other direction, a point here, point C, would be rotated to over there, a point C bar. So if I do a switching around this way, both the original graph and the graph of f reflected about the y-axis would look identical. You wouldn't be able to tell the difference, right? So from a picture, if I give you a graph, that's how you can tell if a graph is even versus odd. If it's true that when you rotate it about the y-axis, the graph is going to look identical to the original one, that's when you know that it's an even function. If that's not true, if you can detect that you have a different graph, something has happened when you rotate it, then it's no longer an even function. Right, so let's do like a quick little, simple little example of that. So let's say that we had, here is the y-axis, here is the x-axis. Let's say that I have an original function looks like this. It's a little triangle there and a big triangle. Let's say this is the original. Well, let's make it a, and then there's like a little, no, let's not do that. Flat, and then like that. Okay, not necessarily a function, but just for the purposes of this picture, let's say that this is f of x. What's it going to look like when I rotate it about the y-axis? Well, it's going to be a rotation around the y-axis. So it's going to have a big triangle out here. And it's just a rough sketch, so it doesn't have to be perfect. A little triangle there, and then it's flat, and then it goes up a little. Right? This is a reflection about the y-axis for this function. And it's supposed to be, sorry, this thing fights me, but it's supposed to be flat along there, just like here, flat around there. Okay, you get the idea. So if this is f of x, then this one would be f of negative x, right? It's a reflection about the y-axis. Here's x. Anyway, I can tell they're different. I can tell that it's been rotated. So therefore, the other thing I can conclude is that this one is definitely not even. Good. If it was something where you could rotate it and they both look identical, like let's say the original function looked like this, maybe it had a little triangle here and then a big triangle, and the other side looked the same, a little triangle here and then a big triangle. Let's say this was the function g of x. Here's g of x. Here is y, here is x. Okay, so now when I rotate it and I move this point over there and this point goes over there, right, I do a swaparoo of points, then I'm going to get something that looks pretty identical. Well, it's supposed to look identical. And I know it's just a rough thing I did by hand, so this one doesn't quite look as mirror image as it should, really, but it's supposed to be the exact same. Okay, let me erase this. I feel like it wasn't as pretty as it could be. So about the same height and then come back down. So it's supposed to be identical. And so when I rotate them, it's going to look identical. It's going to be one big triangle there, followed by a small triangle, followed by another small triangle, followed by a big triangle. Right, so keep in mind I'm doing this by hand and my computer is really fighting me. But there is movement. They look identical, but there is movement. This point here, point A, when we reflected it about the y-axis, moved over here to become this point over here, A bar. And a point right in here, B, in the original function, rotated to become this point over here, B bar. Right, so there was a switching around, but both graphs look identical. So once I reflected them across the y-axis, they looked identical. So therefore, I can tell that this is the graph of an even function. So I can conclude that this one is even. If you can rotate it about the y-axis and the resulting graph looks identical to the original graph, then it's true that f of x is equivalent to its own reflection about the y-axis, therefore it's even. Good. Okay, let's take a look at the other one. That one's a little bit more confusing. This one is saying that for an odd function, the graph of the reflection about the y-axis is equal to, not the original function, but the reflection about the x-axis, right? When we have a negative odd in front, that's a reflection about the x-axis. So this is saying for an odd function, this one is going to be that the reflection reflection about x-axis is equal to the reflection about the y-axis. About the x-axis. Okay, so the reflection about the x-axis equals the reflection about the y-axis. If that's the case, then we have ourselves an odd function. So again, let's do a quick little example of what that looks like, or what it doesn't look like. So let's look at a simplistic example. Okay, so let's say we have let's just say we have a little house over here, like this, roughly speaking, in quadrant 1. We could say that this, oops, let's put it in color, a little house in color. So here's our little house. Right, that's my graph, that's my image. Here's y, here's x. So this is the graph f of x. And I know it's not an actual function, but for this purposes it's fine. And pretend it's a pretty little box. Okay, what would be the reflection of this house across the y-axis? Across the y-axis, if I reflect it, it would end up being a little house over here on this side. So it would come over here and come this way and go like that. So this one would be equal to f of negative x, a reflection across the y-axis. Okay, and what would be a reflection across the x-axis? A mirror image reflection of the function would look like this. It would be down here in quadrant 4, and it would look, whoa, what just happened there? I need to move this one. Okay, so it would look like this maybe. That's still too thick. It would look like this, right? And it would be kind of an upside down thing. Okay, so this one would be equal to a mirror image reflection of that guy. That would be -1 times f of x. Okay, so what can I conclude? This picture, f of negative x, definitely does not look like this picture. So I've established that f of negative x does not equal to -1 times f of x. So this is not odd. Not odd. Good. Okay, so now let's take a look at one where it would work out. All right, so let's go over here and draw another one. So here is y, here is x. Let's look at the function. Let's say the original function was just something that looked like this. Something like that. Okay, so first of all, let's say this is f of x, and we wanted to do a reflection about the y-axis, so we can get f of negative x. So that would come over here, and I'm just looking at this mirror reflection about this axis. So it would come from over here and come this way and go that way, something like that. And that's where these points are traveling this way. This point here, A, is traveling over here to give me this point. And maybe I shouldn't put it in blue. Let's go back to the black. This point right here, A, would be traveling over here to give me this A bar value. And the original value there, B, would be traveling this way to give me a point over there, B hat. Okay, and so this would be the reflection across the y-axis, rotating it this way, rotating it that way, a rotation. This would be f of negative x, f of negative x. Good, a reflection about the y-axis. Okay, clearly f of negative x does not equal to f of x. Okay, but that's okay. Now let's say that we take the exact same graph, and remember I'm just kind of doing it by hand here, so it might not be perfect. But let's say we take the exact same graph, and the exact same graph was something that looked like this. Here's f of x. Okay, and now we're going to do a reflection around the x-axis. So now across the x-axis, this point would travel down here to be over here, and so this would end up looking something like this. Oh, okay, well, it's really ugly, but what we end up getting here is -1 times f of x. That's really, really nasty. All right, let's see. Can I just erase? How far back can I go in the... All right, let's see if I can draw it. It's supposed to be basically this curvature here. So comes down this way and then kind of comes that way, something like that. So this is f of x. And now I want to do a reflection about the x-axis. So it's going to end up looking something like this over here. Where a point here, where this point here, A, traveled across the x-axis to the other side to become a point there, A bar, and a point here, B, traveled up this way across the x-axis to become this point over here, B bar. So this was a movement that way and a movement this way, and so this green one becomes -1 times f of x. Clearly, the green one does not equal the red one either, so it's not equal to its original function, but what we're supposed to get is that the blue one equals the green one. Taking the original function, reflecting it across the y-axis, gets you a different graph, and then if you take the original function, reflect it about the x-axis, gets you a different graph. It's those two graphs that equal each other. The reflection of the function across the y-axis is blue one. The reflection of the original function across the x-axis is this green one. And so these two equal each other. That's how you know that this function is odd, because their reflections across the x and y-axis equal each other. Okay, so f of -x equals f of equals -1 times f of x. So that's how we know that they're odd, right, from the graphs. Okay. This is a good place to stop. We'll pick up on section 7 on Monday.